Let's look at another example. We are looking at one material, B4C, which is boron carbide. We call it boron carbide. It's a ceramic material. It doesn't have metal in it, but two non-metal elements. One is boron, one is carbon in a crystal structure, B4C. And typically this material is obtained quite often by a chemical reaction called CTR reaction. CTR for carbo-thermal reduction reaction. CTR reaction. And the underlying reaction is very simple, as I listed here. Now look at it. See if my chemistry is correct. 2B2O3, which is what? Boron oxide, right? Plus 7C, C for carbon. So it's a reaction between oxide and carbon. Carbo-thermal means you have to heat the mixture up. Carbo means using carbon. Thermal means heat it up. And what are the reaction products? One is B4C, which is a ceramic inorganic phase. The other one is carbon monoxide, CO. Now let's check the balance. Is it balanced? How many boron on left side? 4. How many on the right side? 4. How many carbon on left side? 7. How many carbon on the right side? 1 plus 6, 7. How many oxygen on the left side? 6. How many oxygen on the right side? So it's a balanced equation. So chemistry is okay. So this is the underlying chemistry. Okay. And then quite often we would ask ourselves, how do we control microstructure, or sometimes we call it micromorphology, for this reaction, or for the phase transformation process? Transformation from what to what and what to what? Transformation from one oxide plus carbon into a so-called boron carbide. How do we understand and control the microstructure change from left side of the reaction to the right side? Questions? Okay. So here I show some observations. One is, okay, I'm showing SEM image. The scale bar is 10 micron. Okay, 10 micron. So what we are seeing here are pure boron carbide. How do we know it's pure? Well, you learned the analytical technique, X-ray diffraction. Okay, by X-ray diffraction, very high intensity, sharp peaks. Okay, and of course there are other tools. We know pretty much it's almost, I would say almost pure boron carbide. But I call it structural non-uniformity. Do you agree? Just from this couple of hundred micron wheel, I'm seeing some of the boron carbide look like this huge crystal, right? Some of them look like this like a dagger or sword. Some of them look like these equi-axed shaped crystals, and these are highly faceted. Quite often means they are highly crystalline. Makes sense? But some of them, if you go zoom in, we have ICM, a powerful magnifying glass. We zoom in, we may find even here that you can find even so-called nano-sized particles, and also crystalline. How do you know? We have also done transmission electron microscopy. Look at the lattice diffraction. You know it's all boron carbide, but highly non-uniform. How did we get it? We said, okay, we get it by carbo-thermal reduction under what condition? 1450. Okay, pretty high temperature, above the melting point for many metals, for 3 hours. In a conventional tube furnace, a furnace inside a tube, which provides so-called atmosphere control. Okay? And then when we did the experiment at a different condition, 1750 degrees C, for only 3 minutes. We raised up the temperature, we decrease the time, raise the temperature by 300 degrees C, decrease the time by, I don't know, 60 times, right? And using a so-called microtubular reactor. Why? Because we want to control the reaction time to be short. And look at what we got. Again, what is the scale bar? Still 10 micron. Okay, so roughly the same magnification. You see what I mean? But now you look at the microstructure. You would call this pretty much, compared to here, uniform, right? Pretty much uniform. I'm not cherry picking, it's representative. Uniform. And every one of those grains, they are still pure boron carbide. How do you know? Still by X-ray, by transmission electron microscope. But every of those particles are around 0.2 to 0.4 micron, 200 nanometer, something like that. Okay, so you see, for the same chemical reaction, by doing it at a different condition, we get a different so-called microstructure or micromorphology. And it, as an engineer, you may want to understand and also want to control, because you may have customers who tell you, I want everything to be uniform. On the other hand, for certain application, you may want large grains. Maybe you want to promote the growth of these things. So that's where this class will come into play. Okay. So again, let's still look at the same reaction. B4C synthesis or formation by this so-called CTR, CTR for carbothermal reduction reaction. We ask ourselves, we did the reaction at 1450, and we also did it at 1750, one for longer, one for shorter. We ask ourselves, as the reaction temperature goes even lower or goes even higher, what would happen? Okay. And of course, the first thing that you want to consider would be look at the thermodynamics, look at the so-called free energy change, equilibrium free energy change. So what we are plotting? We are plotting free energy change, in particular Gibbs free energy change versus reaction temperature. And if you learned in your thermodynamics, you can pull out the data from quite often standardized table to get a Gibbs free energy, either standard Gibbs free energy, or you assume certain partial pressure of the stuff. And then we can get a line, we can plot it. What does this mean? If I say this is 0, this bottom is negative, top is positive. So what does this mean? The temperature, as the temperature goes higher and higher, the Gibbs free energy change for this CTR reaction is more and more negative, which means the reaction has greater and greater tendency to proceed from left to right. Make sense? On the other hand, if we are lower and lower temperature, the Gibbs free energy change is positive for this, as we write from left to right. It means what? Gibbs free energy is positive means the reaction doesn't really happen. Make sense? The reaction doesn't really happen if I'm at 1600 K. It's a huge positive number, which means at least under whatever you are assumed partial pressure, it doesn't go. Make sense? That's what you learned in thermodynamics. Okay. Now let's consider the microstructure a little bit. At lower temperature, we said 1450, highly non-uniform, but pure. 1750, uniform, not pure. Still pure, sorry, but finer grain. We did it at lower temperature, even lower, 1150 for even longer time. Now this is what we got from tube furnace. We have grains. Each of these grains may be, I don't know, 5-10 micron, pretty large. And then we have this. It seems to me like potatoes or carrots growing out from the soil, right? It's literally like growing out from the soil. You see this? In some of them even embedded in there. It's forming. We are capturing its formation process. And what about phase purity? Well, we said that's some boron carbide. But pay attention to this word, trace, which means when you do X-ray, the majority is not boron carbide. The majority is actually these types of very smooth amorphous host matrix material, which is essentially boron oxide amorphous plus amorphous carbon mixture. That gives you this smooth feature, amorphous mixture. But out of it, we are growing, like potato growing out, like carrots growing out, some of the highly crystalline crystals. But it's occasional. As a result, our X-ray don't show much boron carbide. Make sense? This is what we got when we further decrease the temperature. And then look at the thermodynamics. Does that make sense? When the temperature goes lower and lower, the driving force of free energy change become more and more positive, which means it doesn't really want to happen. Make sense? On the other hand, we tried, not we actually, some other people tried this experiment at even higher temperature. Previously we tried 1750, but some other people, they have better technique. They can go to 1900 degrees C, but only for 1 second. Only for 1 second. And this is what they got. Okay, they are no longer using SEM. They are using a transmission electron microscope, TEM, which can go to even higher magnification than SEM. And what they observed is around, I don't have the scale bar here, roughly 20 nanometer uniform, consistent nanopowder. Make sense? So that's what they observed. And then the thing is, if you are a production engineer, if your customer wants uniform nanopowder, which condition you try to go to? Definitely not here, right? You try to go to here because this one gives you the uniform nano powder. Make sense? So by studying kinetics and phase transformation, we are going to go beyond the thermodynamics to try to understand how do we link the process with their resulting microstructure. And by this understanding, we can the actual use would be better control of production, of manufacturing. Okay? This is pure boron carbide, uniform nano-sized powder. You get it at very high temperature, but very short period of time. Okay,